Okay, hello everyone. So today I'm going to be going over the 2019 topic 10 questions. So we'll start off with May 19 time zone 1, and question 5 is related to topic 10. It's gravitational fields. So we're talking about the moon Phobos moving around the planet Mars in a circular orbit. Okay, what is the origin of the force that acts on Phobos? That's not a very difficult question. It's the gravitational force due to the gravitational field of Mars. So let's write that down. It's the gravitational force due to Mars's gravitational field. Outline why this force does no work on Phobos. Well, we should know that whenever something is moving around in a uniform circular motion, then the centripetal force does no work because it's perpendicular to the instantaneous displacement. So in a circular orbit, the centripetal force, here it's gravity, does no work. In a uniform circular orbit, we might add, in a uniformly circular orbit, the centripetal force, here gravity, does no work perpendicular to displacement. They don't give us a lot of space to write things down in. Okay, next one, orbital period satisfies this, where r is the average distance between the center of the planet and the center of the moon. So this is Kepler's third law. Kepler's third law, which often pops up. So it's really good to know the derivation of that, and it's very simple. And it is simply that the force acting on the moon is, of course, the force of gravity, which is this. And that is equal to the mass times the acceleration, the mass of the moon times its acceleration, and the acceleration is the acceleration of uniform circular motion, which is v squared over r. And then we just have to cancel and rearrange. Cancel 1r, like that. And then what do we have to do? We have to remember that the speed is the circumference over the period to get the period involved in this, and eliminate v. So we plug that in, and v squared gives us 4 pi squared r squared over t squared. And now we're almost there. We can simply divide 4 pi squared over, and then we multiply r over, get r cubed over t squared. And there you go, right? So that shows us that k is g over 4 pi squared. Okay. Next one, we continue with the Mars-Phobos system. And we're given the mass of the Earth. Then we are given sort of ratios between the moon planet distances and the orbital period ratio as well. So we often work with ratios in astronomy, and here the way we can sort of figure this out is to notice that the constant k that we just derived, is a universal constant. You can see it's expressed in what's going on. It's a g over 4 pi squared, so that's going to be constant. So k is the same for both systems. So if I rearrange, then we know that k is r cubed over m t squared, and that has to be the same constant for Earth, Moon, and Mars, Phobos. So for Earth, Moon, we can sort of write em for Earth, Moon, and then as Earth's mass, that has to be the same as r over m r cubed over mt squared for Mars-Phobos system, where m is Mars. So we know we have this equality, and we want to find the mass of Mars. So let's just get that up, and then we can start isolating. So RMP, let's divide by REM. That ratio is going to be cubed. We multiply by TEM squared, so get TEM over TMP squared multiplied by the mass of Earth. And then now we're almost there. Simply just plug in the ratio. So Mars-Phobos distance is 41 times less than the Earth-Moon distance, right? Or Earth-Moon distance is 41 times greater than the Mars-Phobos. So if we put that in, we get a ratio of 1 over 41 has to be cubed. And then orbital period of the Moon is 86 times, so Earth-Moon system, so that's going to be 86 to 1. Square that, and then the mass of the Earth is given. And then we get the mass of Mars, which I remember is sort of roughly a factor 10 less. Okay, Earth is 6 times 10 to the 24, Mars is 6 times 10 to the 23, 10 times lighter. Okay, then we have the Earth-Moon potential graphed here, and we have to find the mass of the Moon. So what we have to remember is that when we look at a potential, so the sort of maximum point of the potential is where the slope, of course, is 0, and the slope is equal to the net gravitational field strength. So that is 0 there. So basically the Earth and the Moon, they're sort of pulling in a mass that is placed at that point with equal forces in opposite directions. So this is the point that we'll use in order to find the mass of the Moon, because we know that we can read off, first of all, that that is around 0.9 of a distance away from the center of the Earth. You can see it's 0.1 of a distance away from the Moon. So let's just say at a distance of 0.9, we have the net gravitational field strength is 0, and that implies, of course, that the gravitational field strength due to the Earth at that point, which can be expressed in this way, is equal to the gravitational field strength of the Moon at that point, which can be expressed in this way. And of course they're in opposite directions, so G is really a vector quantity, and it's pointing in opposite directions, but here we're just working with the magnitudes, and G cancels out, and the mass of the Moon is of course going to be 1/9 squared the mass of the Earth. So that's like roughly 100 times less, and you plug in the numbers, you get this. Okay, then we're moving on to May 19 time zone 2, and the topic 10 question was also on, well, the first one was on gravity. Next one is electric fields. So we have a planet is in a circular orbit around a star. Gravitational potential at the position of the planet is V. Remember, V is minus G M of whatever is being orbited, what's creating the field, divided by sort of the distance to the point you're looking at. Show that the total energy of the planet is given by that. So that's total energy. Now, one that's really good to remember is total energy is half the gravitational potential energy. Let me just show you the really important graphs that you need to remember when it comes to orbital motion. So here we have energy versus distance away from the center of whatever's creating the gravitational field. So I always remember kinetic energy is positive, and it decreases in this way. Now the total energy is the exact opposite of that, so it's negative the kinetic energy. So it's just a mirror image in the x-axis, and then the gravitational potential energy is twice the total energy. So I always have these graphs in mind when I'm doing these questions. So total energy, as you can see, is half GPE, and then we know that GPE is minus G m over r, and then we can see that if I take little m, the mass of the planet, out of that, we are left with minus Gm over r, which is V, the potential. So there you go. Suppose the star would contract to half its original radius without any loss of mass. Discuss the effect, if any, this has on the total energy. So won't have any effect, right? Because the potential only depends on the mass and the distance to the center of the mass. So if there's no loss of mass, we sort of have, you know, the same gravitational field, and the planet is at the same position as it always was, so there's not going to be any change. So we can write would not change anything. Since V, the potential, remains the same at the position of the planet. You know, star has same mass, only depends on the mass and the distance to the planet. Okay. And then the next one is on electric fields. So we have two fixed charged particles, and we have an amount of charge q on x and little q on y. Distance between x and y is 0.6 meters. Distance between p and y, 0.820 meters. At p, the electric field is 0. So, okay, again, we have the two electric field strength vectors must balance out. They cancel out, right? Equal and in opposite directions. So the magnitude of the electric field strengths at that point have to be equal. So we can write down that the magnitude of the electric field strength due to x at that point is going to be kq over the distance to p from x, which is 0.6 plus 0.820, and that has to be squared. So that electric field strength vector magnitude is going to equal to the electric field strength due to y at p, and that's going to be this. Use the same formula, and then you can see it's relatively straightforward to get the ratio. K cancels out. Just need to do this calculation, and that gives you around 3. Now, you could say that they have to have opposite signs, obviously, so you could perhaps write that as -3, but I checked the mark scheme and it doesn't really matter. So yeah, just in magnitude, the ratio is 3. Okay, there you go. See you another day. Bye.